Hello, welcome to this segment for drinking water treatment plant operators exam preparation. And today we're going to be covering corrosion control, a pretty long subject, lots of material within there, and a lot of chemistry. And we'll try to keep it as basic as we can for all of you getting ready for your either C or B or your A drinking water exams. And a lot of people have commented that this material seems like it's much more conducive for distribution systems than actual water treatment. But remember that your drinking water license does supersede distribution system licenses. So this material is very important as you may be a person on the scene during a water main break repair or disinfecting a water tank or a water line. And you will definitely need to know this material because it's a big part of water treatment, and corrosion control and prevention is very important for the infrastructure that we have under the ground and also in the treatment plant. So we've got a lot to cover today. I hope you have your cup of coffee ready, and I do, and we'll take probably a break at some point. And as you guys are watching this video, you'll be able to take breaks whenever you want because you can just start and stop. But as I make this, I'll probably take a break at some point. Anyway, let's go ahead and jump in. So we have our copyright statement, the University of Florida Center for Training, Research, Education for Environmental Occupations, which is what TRIO Center stands for. All rights are reserved. No parts may be reproduced, stored in a retrieval system, or transmitted in any other form, electronic or otherwise, without prior written consent of the copyright owner, which is the University of Florida TRIO Center. Anyway, my information is here, and hopefully you can kind of see it over my shoulder as we go through the presentation. And my name is Ron Trigar. I'm a senior training specialist here at the University of Florida TRIO Center. My contact information, the best way to reach me really is by email, which is shown here. It's rtrigar@trio.ufl.edu. And my phone number is shown here to certainly leave me a message if you'd like. And by all means, go to our website and check us out online at uftrio.org. All right. So a few things we need to cover first before we actually jump into the discussion about corrosion. Um, we need to make sure that you all are familiar with some terminology, and this gets a little confusing at times because of other processes and other words that are used in water treatment. Sometimes they kind of blend together, so hopefully we'll be able to clear that up for you guys. So the first thing we want to talk about is the word tubercle or tuberculation. A tubercle is a lump or mound of rust on a pipe surface or a piece of metal surface. And I've got a little bit of demonstration stuff here. So I'm going to kind of show you what a tubercle looks like. And hopefully we'll be able to see this with the camera. I'm going to show this up to the camera. And if you can see inside of there, kind of get a little closer. Hopefully you can see that. There is some rust forming on the inside of this pipe, and they're big and lumpy looking. And these big lumps of rust are essentially the metal pipe kind of changing form. The iron was, mined out of the ground, and it was melted and cleaned up a little bit with in a foundry, and a little bit of added metals are added for out to make an alloy. But essentially the iron is coming out of or changing shape, so to speak. The pipe was made as a nice round piece of metal, and as it corrodes, the tubercle starts to form where the iron is actually changing shape or form. It's kind of coming out of the pipe structure itself. So it's a lump or mound of rust that forms. And the process is actually called tuberculation. The place where this tubercle starts to form is known as the anode. The anode is the point or a place in a piece of metal or on a piece of metal, especially inside of a pipe, where the electron activity starts to get moving. And one of the things that we like to talk about in our classes here at Trio Center is how these electrons move and how they use the metal of the pipe to start flowing, which is very, very similar to electricity, the way electricity or the electrons move through copper wire. So the anode is where the actual form of or the formulation of the formation of that tubercle starts to form. So that's important to remember. That's where the lump is going to be found. The cathode now is a point or piece of metal outside that area of the anode, just outside the area of the anode. It can be right next to the anode or a little bit further away, but we're talking about microns, millimeters, fractions of an inch, where the cathode is a point on the piece of metal where the electrons can essentially escape the metal that of the pipe or the structure of the metal inside the water, and then they flow into what's known as electrolyte. Now, in our case, in water treatment, electrolyte is the water that we've produced for the drinking water purposes. So the electrolyte, even though it's a term that sounds very fancy, it's really just the water that's moving through the pipe. Now, the more dissolved particles that are in that water, the more prone it is to actually getting these electron activity flowing. So think about particles or salts in the water, similar to say TDS, or total dissolved solids, or salt that makes the water conductive. The salty water is a little bit more conductive. If there's actual salt material in there, it will actually make the water more conducive to electricity flow. So the cleaner the water and the less solids that are in there, the less likely it is to be conductive. We can measure this as conductivity, in case you were wondering about that. So the four terms that we see here: tubercle, anode, cathode, and electrolyte. Those are all important components of corrosion, and this happens a lot in iron pipe, cast iron pipe, galvanized steel pipe, ductile iron pipe. Anything with the metal iron in it is definitely prone to this type of corrosion. So we'll go ahead and continue on. I've got a few more things to talk about here as defining this situation. Tuberculation, I mentioned already, is the formation of these rust lumps inside of a pipe. You can see in this picture, if I can kind of take a second to highlight something for y'all, you can kind of see in this picture these lumps of rust that are forming inside this well casing. Looks pretty chunky and lumpy inside of there. You can kind of imagine that the pipe surface is very rough. So these terms that you see here, first one we see is tuberculation. It's the formation of the tubercles, and what tuberculation causes for us is a loss of the pipe's ability to carry water through it or move water at a good velocity. And when that starts to happen, we lose water volume through the flow being slowed down, and also we lose pressure because of all these giant mounds of rust that are forming. The internal pipe roughness starts to increase. Now you can kind of tell that this piece of pipe in this picture is very, very rough, and you can imagine that that probably was not the way it looked when they bought it from the factory and installed it. It was probably nice and clean and smooth. So over time, it had gotten these rust lumps inside of it. So this tuberculation is causing the C factor, or a factor that's used to describe the smoothness of the pipe. And the C factor is decreasing in value. So C factor, say, of 40 or 50 is much rougher than a C factor of, say, 150 or higher. So the C factor is being decreased because of the internal roughness of the pipe, which reduces the distribution system pressure. And by the way, it also increases the frequency and the amount of leaks in the pipe. Now, if if you can also imagine with me as we go through this discussion, that if this lump of rust that's kind of forming on that side of that pipe, if that lump of rust was to say fall off or flake off of the pipe itself, because it's actually kind of fragile. If the flow picks up a lot, if we're flushing the lines or a fire breaks out and the firefighter's using a lot of water, that water movement tends to break off these tubercles, and the tubercles then start flowing through the pipe. Well, they're bumping into and crashing into other tubercles, and they end up hitting these other tubercles, and they start breaking this stuff off the pipe. Well, what it does is it just exposes the fresh pipe underneath that tubercle to more ability to corrode, to make more rust. You know, with the amount of oxygen that might be in that water, we start to form more rust. So when this process keeps happening over and over and over again, the actual pipe wall thickness underneath that tubercle is getting thinner and thinner and thinner and thinner. So you can imagine again that if you got a very fragile pipe or a very old pipe where the wall thickness is getting thinner, that as soon as any pressure increases or water hammer occurs, that's when we start to break the pipe open and have what we call a leak. Now, most of you probably know that leaks don't occur when we would like them to happen, which is never, by the way. So leaks do happen, and they usually occur, at midnight on the rainiest day of Christmas Eve or something like that. They never seem to occur on days when we're ready for them. So they end up being emergencies, and sometimes we lose water pressure down below 20 psi and have to issue precautionary boil water notices, and then the whole thing, just keeps snowballing. So these leaks and this tuberculation is very, very serious for us as water operators. So the corrosive water tends to allow materials to go back into solution. So we're going to be talking in this segment about the marble test. We're going to be talking about coupon analysis. We're going to be talking about the Langler Index. And that's going to help us determine the corrosivity of the water. And the more corrosive the water might happen to be, the more prone it is to allow these metals to deteriorate and, so to speak, dissolve back into solution. So then what happens is we have this red water complaints, black water complaints from manganese and some of these other pieces of metal coming off, particulates that get trapped inside of the sink aerators or the screens at your homeowners and residents and consumers, sink faucets, and sometimes the water actually comes out a little red to begin with, especially if the water is corrosive, because that's actually dissolving some of that iron back into solution, which the iron then gives it a little bit of a red tint. The water tends to take on a metallic, bitter taste. It does tend to not taste as aesthetically pleasing, maybe, as water that doesn't have this occurring. And obviously, the chances of water main breaks are definitely there, and that's what we really are trying to prevent, because this water main breaks never usually they don't seal themselves off. They get worse and worse over time, and it ends up accruing in our water, unaccounted for water. Let me say that we are producing water out of a well or a water plant, and these leaks are not being accounted for. So the amount of unaccounted for water percentage keeps climbing and climbing and climbing, and eventually we're in much over the 10%, maybe up in the 20-30% unaccounted for water, which is a waste of valuable water supply. So obviously you can see in this picture we have a water main that's being repaired. This was a break, and I'll kind of point out to you here the crack or the break is right about there in the pipe, and you can kind of see that they're already starting to make a repair. They're cutting with a cutting tool. They're cutting through that pipe to take out that segment that's all broken. And this is what happens when we don't pay attention to leaks. Now, you can probably go online and find all kinds of pictures of water main break and pavement damage and roadway damage. You can find them on any internet search. This one happened to come from the city of Los Angeles, and this was the result of a huge water main break. The fire department showed up to try to cordon off the area and protect people from, driving through this amount of damage to the roadway. But it looks like it actually started sucking in the fire truck as well. So, and when we're in the class together and I'm talking to you guys one-on-one, I'm always joking about this picture and kind of saying, I don't know exactly what that firefighter is trying to do there underneath that truck, but whatever it is, it's not that important. And they make these things called poles and, fire hook, and you can just pull out whatever you need to get. So I'm not sure what he was trying to do in that picture, but it sure doesn't look safe to me. All right, so the process of corrosion, there's several things we're going to talk about. We're going to talk about galvanic corrosion, electrochemical corrosion, erosion corrosion. But just imagine, if you will, corrosion is the changing or the decomposition of a piece of metal and basically turning it into another form of the metal, or even just dissolving it completely. So corrosion is very damaging to water mains, water structures, even just the rust that occurs on water storage tanks, elevated storage tanks, that has to be kept under control because we have valuable pieces of equipment out there. We call all of these things our assets that we have available to us. Water pipes and hydrants and all that are valuable assets. We need to protect those. So corrosion is the gradual decomposition or destruction of material as it reacts with water. And you notice here in this picture it says metal, which is the pipe, or cement lining, which I'm going to get to a little bit later, because a lot of our pipes are coated with a grout that protects the metal from the corrosive components in the drinking water itself. So the metal or the cement lining is kind of like a protective barrier. The severity and type of corrosion depends on the chemical and physical characteristics of the water and what the pipe material is. Now, obviously, we've switched a lot of water system piping to PVC or polyethylene or some type of material like that. So we see different types of corrosion occurring mostly in this discussion with our metal pipes. So again, the ductile iron, the steel pipes or the galvanized steel pipes, or the plain old cast iron pipes. All right, so we have 4 types of corrosion. We're going to cover these and have a few quiz questions as we go through. So the first one that we're going to discuss is electrochemical corrosion. The electrochemical corrosion process is the result of what's known as an electrochemical reaction. Metallic corrosion in water mains and water pipes and water structures is always the result of this electrochemical reaction, which is essentially electrons moving through the metal when they become agitated or excited by the water, the electrolyte moving through the pipe that has some dissolved solids in it, which tends to make the water conductive, which tends to get this whole thing in motion. So if you were to remove the water from the water pipe and you never put water through it and it didn't have that exposure to it and there was no electrolyte, then we wouldn't have the corrosion. We would have, a piece of pipe sitting there in the yard ready to go. But it's when we start putting water through it that we start to have the problem. So the flow of the electric current is an essential part of this reaction, and it is actually excited or generated, if you will, by the electrolyte that moves through that water, through the pipe. So in the electrochemical corrosion process, we have the term anode and cathode reappearing, which we talked about a little earlier. The anode, remember, is where the tubercle forms, right? And the anode is known as the positive pole, or in case of a battery, think about this D-cell battery here. We have the positive pole at the top of the battery. So the anode is where the anode and the cathode have to be connected, by the way, and we're going to talk about that a little bit in a minute. But the anode is where the process begins and where the electrons start flowing away from the metal. So the pitting, or the actual tuberculation, starts forming at the anode. So in this piece of pipe, now this is a drawing of a piece of pipe, and what we're trying to depict here with this picture is that we have a piece of iron pipe. It's one stick or one cell of iron pipe. It's maybe a foot 10 feet, doesn't matter. It could be 2 inches long. But what we see is one solid piece of iron pipe, and when water is moving through here, which would be the electrolyte, I'm going to put H2O, that has some total dissolved solids in it. As the water is moving through there, it starts to generate this current. And if the piece of pipe is damaged, where we're kind of showing that right there, let's just say that the piece of pipe came from the factory with a small nick in the grouting, or a small imperfection in there, and the electrolyte starts to get the iron kind of in motion, and the electron moves through the pipe to try to complete what's known as a circuit. Now here in this picture, they show the electron, that's the E with a little negative. They show the electron kind of moving outward through the metal and back into the metal. I think most of us would probably recognize that the electron is actually moving through the metal of the pipe itself to the cathode. Now remember, the cathode can be here or here. The cathode can be in different places. It just depends on the pipe material and the activity of the electron. But anyway, the electron flows through the metal of the pipe. It leaves the pipe itself, the metal, and joins the electrolyte. The electron itself, let me erase some of this stuff that I got here. The electron then wants to complete the circuit. So remember, the electron is in there. So we want the electron to complete the circuit. And when it does, it flows backwards to the anode. So the electron is basically like an electron moving through your copper wire in the house wiring system, electrical system of your home or business or wherever copper wire is. So it's completing a circuit. So that's what's happening inside of an iron pipe. Now remember that the electrolyte needs to be there to make this thing start to occur. The electrochemical reaction is where the actual electron moves from a point known as the anode to the cathode. It leaves the cathode, joins the electrolyte, and comes back around to the anode. So it's completing a circuit. So remember these couple terms: the anode, the cathode, and the electrolyte. The electrolyte is much more conducive to moving these electrons if there's some dissolved salts in there, and the more TDS or dissolved salts that are in the water, the more chance of this occurring. So the cathode and the anode must be joined together. So they are kind of showing here a piece of pipe, they would be joined together here. But the electrolyte, when it starts moving through there, is what really gets it going. So we have an anode, we have a cathode, we have the electrolyte, or the electron, that moves from one to the other. You can kind of see in the red arrows here, it's flowing backward, and we start to form this tubercle, this lump right there at the anode. Now I'm showing two batteries here. Looks like we have some AA batteries showing up here. Remember that the anode is the positive pole, the cathode is the negative. So if we take a piece of wire and we connect the wire from the positive to the negative pole on these two batteries, we would start forming or joining the cathode and the anode. The actual electrolyte, when it's there in the water, really gets the whole process moving, which would be similar to hooking up the bottom part of the batteries, the positive and the negative, together there. We would have a really good flow of electron activity here in that scenario. So what ends up happening then is we start to now have the degradation of that actual piece of metal pipe. If you're thinking about how batteries work, in this particular case we're showing here to the right, the batteries would end up losing their electrical carrying ability, or electrical generation ability, because of the dissimilar metals in the battery, and the battery would essentially, what we would call, be dead, because the electrons and from the different metals reached what we know as equilibrium. So the batteries then are dead. It doesn't produce any more electricity. So the multi-layered rust deposit that formed at the anode is known as a tubercle, and the whole process is known as tuberculation. Again, you see this is in red, it's bold. That's a key to tell you that if you're watching this video and you're studying for your A, B, C, or even a D exam for drinking water, you need to know what electrochemical corrosion does and what tuberculation is. All right, so there's that. So let's take a look at a piece of pipe again. So we had the anode and the cathode being joined, right? The anode and the cathode was joined, and we had it coming back around. Well, when the electron flows back around, it actually starts to precipitate out some of the ferrous iron right back at the point where the anode is. So it starts to make a particle uh, of iron deposit right at the anode. So if the water's flowing through here at a pretty good velocity, it sometimes tends to scour off the tubercle that starts to form there, and sometimes the tubercle is broken off and it falls down. It kind of falls down into the pipe, or it tends to bump into other anode pieces of tubercles. But we're essentially now with a fresh piece of metal right there at that anode. So the more fresh metal that's exposed to the water and the oxygen in that water, which is a big component we're going to talk about in just a minute. But if there's oxygen in that water and you've got water and iron together, man, you're going to make rust like crazy. So the more exposed metal there is to the oxygen, the more it starts to rust. The anode is where the tubercle forms. The anode is also usually where the leak happens, because that's where the pipe wall thickness is getting thinner and thinner and thinner. So again, the tubercle starts to form. Now, if the water velocity is very slow and this is occurring, then it could form a multi-layered tubercle, which we discussed a little bit earlier. The multi-layered rust layer is the tubercle. Again, if you go and flush the line, because we like to flush the line when people complain about water complaints, odors and things like that. So we flush the line and we end up breaking off some of these tubercles. You can kind of see that they're kind of disappearing again off of that piece of pipe. Now all of a sudden we've got this fresh metal exposed to the water again. So this thing just keeps happening over and over and over and over. And when that finally occurs to the point where the pipe wall thickness, when the inside diameter of the pipe exceeds the outside diameter of the pipe, we have what's known as a leak or a hole in the pipe, because that really can't happen. You can't have the inside diameter exceeding the outside diameter, because that's impossible, right? So that's when a leak occurs, and that's when a hole forms in the pipe. So anyway, that's my attempt at humor. So let's take a look. We have a well casing here, and the well casing, you're kind of looking down at the water level in here with a camera, and you kind of see the water down there in center. And look at all the lumps all over the place on this piece of iron pipe. All of those pieces of lumps of rust are known as tubercles. Underneath those is where the anode is placed, and when these lumps of rust fall off of there, they will expose the metal to fresh water movement through there again and again and again. So that's a good example of a very tuberculated piece of metal pipe. All right, so electrochemical corrosion. Again, the carrying capacity of the pipe is reduced. We can't get the same volume of water through it. People start to complain about low volumes of water. They don't get the same pressure that they normally have, so the pressure starts to fall, and we lose what's known as, or we decrease the C factor. Remember, that's the internal roughness, or rather smoothness of the pipe. Um, and we start to get red water complaints, things like that. So all of these things that you see on this list, all these bullet points that are here, are very important for you to recognize that these are all indicators that corrosion is happening somewhere in your water system. So all right, so let's move on. So any questions on electrochemical corrosion? If you're still not sure of something, or something seems a little bit fuzzy, go back and watch the video again. Contact me if I can help clear up anything for you. All right, the next thing we want to talk about is a form of electrochemical corrosion, and this is known as galvanic corrosion. This is a little bit more, I think, readily visible and a little bit easier for you to visualize, because essentially we're going to be talking about two different types of metal pipe touching each other. So if you have let's say a backflow preventer that's made of brass, or some alloys of brass, and you're threading that backflow preventer onto a piece of galvanized pipe that's got threads on it. Well, now you've just touched two different types of metal alloys and metals together, and the electrochemical corrosion starts to happen at that point. So it makes the corrosion start to occur. One of the metals that's weaker will become known as the anode, and the metal, whatever the metal is that's a little bit stronger or a little bit tougher or a little bit more durable than the other will be known as the cathode. So they'll assume the role of anode and cathode, depending on where they fit on something known as the galvanic series. So it's a complex form of electrochemical corrosion, but definitely seen by a lot of you. I know that you've probably witnessed this at your water plants. The dissimilar metal, these two metals are dissimilar from each other. So the metal that's higher in something known as a galvanic series becomes known as the anode, and the metal that's lower in the galvanic series or the galvanic list of metals is the cathode. So when we start joining these two things together, we start finding a lot of current occurring and then metals deteriorating. So we have this list right here. You can kind of see it says galvanic series. The galvanic series is topped off here at the top where it says the most active metals. And down at the bottom, we have the least active metals. So the least active is the cathode and the most active is the anode. Now take a look over here for some anodes. Pieces of metal known as magnesium or zinc are commonly used in water treatment plants, water treatment tanks, basins, on marine engines and boat engines. We have these things known as sacrificial anodes that we put in these tanks to allow the corrosion that would occur naturally to attack a piece of metal that we generally say, okay, it's a cheaper piece of metal to replace than the whole tank is, or the piece of stainless steel that we're trying to prevent the corrosion occurring on. So we end up putting some things known as sacrificial anodes inside the tanks purposely, or on the water pipes purposely, to allow the corrosion to occur there rather than on the metal pipe. So take a look at the list. We got magnesium and zinc at the top. They're very, very active metals and will corrode somewhat quickly given the right circumstances. As we go down the list, as we start heading south on this list, we end up going towards the more or least active or more cathodic metals. Obviously down here, look at this, we have gold at the very bottom. Well, we don't have too many water mains made of gold, but we do have water mains that are made out of, say, cast iron. We do have water mains that are made out of steel and coated with zinc, which we generally call galvanized pipe. And we see nickel, brass, copper, all of these types of metals, or these metals are found in a lot of our water mains and a lot of the alloys that our water pipes are made of. So what we want to pay attention to here is that when we join together pieces of metal, oops, I'm sorry, I'm going to go backwards here real quick. When we join together pieces of metal known as an anode and a cathode, let me go ahead and erase these, and we're going to spend a few seconds talking about this a little bit more here. So we're going to, sorry again, and let's go back to our pen. Now, so what we see is, let's say that we have a piece of metal pipe that is steel, and it's coated with zinc to make it be what we would know as a galvanized piece of pipe. And we're going to thread that piece of metal onto a brass valve, gate valve, some type of equipment. When we thread those together, the electrochemical corrosion could start to occur if we don't do something to prevent them from touching. But brass is lower on the list, so the brass takes on the role of the cathode, and the steel pipe coated with zinc, these are coated together and kind of clinging together. the zinc and steel tend to take on the role of the anode. Now, which is the softer, most um, expendable metal? Well, the zinc is, and the zinc tends to start coming off of the galvanized pipe, and we start to expose the steel. Well, guess what? Now we start to have the steel corroding. So you can kind of see that this activity would occur, and if we don't pay attention to it, we could then have the pipe actually falling apart, and sitting there without any damage is the brass valve or whatever we threaded onto that piece of pipe. So hopefully that clears up a little bit of that for you guys. Now, water systems generally aren't made of gold, right? And we generally don't have just zinc pieces of pipe out there, but we do use zinc as a sacrificial anode. So what you're seeing here in this picture or this table is metals that are commonly seen. We see stainless steel. Stainless steel is down here listed as the cathode or most cathodic, and then we see as we go up here, we see cast iron, steel, zinc. So those become more active, and those will corrode or deteriorate more than the stainless will. Now, the higher the level activity, the greater the tendency for the metal to corrode. Now, what that means is the further apart these metals are on this galvanic series, the more the activity tends to occur, and the more the corrosion starts to happen. So, just want to kind of pay attention to that. The actual metal pipe is returning to its ore state. The ore state is when it was a piece of iron that was mined out of the ground and then heated and formed in a mold to make a piece of pipe. So sacrificial anodes are known as basic or base metals, soft metals that are very active in the galvanic series. And again, the sacrificial anodes are commonly found in zinc and magnesium. We've got a picture here of, looks like a couple of outboard engines in a hooked to a boat, and those are submerged in the water. The propeller and the foot of the engine are down in the water. They're all made of generally preformed or fabricated, molded metal shapes. Like the engine itself is usually cast aluminum or something similar. So, we have all these different metals touching each other in these engines and on our water plants. Back in the water plant, we actually have the pieces of metal mixers and flocculators and things like that down inside the water. So we don't want those to corrode, so we attach a sacrificial anode to that metal. So one thing that we want to be clear about with everybody here that's paying attention to this video is we have to always kind of come back to the fact that in older homes built in the 60s, 70s into the 80s, a lot of water pipes and plumbing in the home were made of copper or used copper inside the water, or inside the home rather. So we have copper pipe that's, so to speak, sweated together or welded together with lead solder or tin solder to hold the copper and the copper pipe together. So in this picture, you can kind of see right here at this joint, we see where the copper was joined together with lead solder. So what will actually happen when we start connecting these different types of metals together? So remember, we said about the galvanic series, right? What's going to happen? Well, one of those metals will take the role of the anode, and one will assume the role of the cathode, and one will start to deteriorate before the other will. What you'll notice is that the lead solder is the more active metal and will start to deteriorate before the copper was. So the copper actually becomes the cathode, the lead solder or tin solder would become the anode, and the actual pipe will start to deteriorate, the joints will start to deteriorate rather, and the pipe will actually come apart. And you'll start to experience leaks under the home or in the walls or in the slab and that kind of stuff. So what we see in this picture is that we have copper pipe at the top, and this same type of copper pipe with lead solder has been replaced here in this picture with something known as CPVC, which is chlorinated polyvinyl chloride pipe, or CPVC, which is generally used in hot water heater installations and hot water lines in the homes. So you see that being the go-to replacement in some cases. So So what will happen? The pipe will fall apart and you'll have leaks in the house. All right, so preventing galvanic corrosion. So since the anode and the cathode must be joined together, it makes sense to say, well, if we don't let them touch, then we won't have the corrosion, right? Well, if we don't let them touch, then we don't have a solid piece of pipe and then we have leaks. So we have to have them touching somehow. So we separate them using a piece of insulating material between the two metals, and we call that material, we call it dielectric material. Dielectric material is an insulator to prevent the electrochemical reaction between the two different types of metal. That are touching. So here's a good example of what I was talking about a little bit earlier. You see in this installation a valve, a gate valve that's made of brass. So here's the brass gate valve, and it's essentially threaded to a piece of galvanized pipe, and you can clearly see, I hope, that the amount of corrosion that has been occurring there in these threaded areas. You even see it has some rust look to it. It actually even looks rusty. So you can kind of see that's that metal coming out of solution, so to speak. It's coming out of formation. So what we need to put there is a dielectric union. So the galvanized piece of pipe would be threaded into this piece of the dielectric union, and the dissimilar metal on the other side, the brass or whatever it is here, we'll just write over the word galvanized, G-A-L-V here, and over here we'll say this might be brass, right? And that would be threaded together or coupled together. So now what you notice here is that there's inserts between the bolts that are holding this together. The inserts are the dielectric material. There's also a gasket here. There's a gasket around here. Now that's dielectric material as well. It might be some type of rubber or neoprene or something to keep that metal from touching each other. If you don't use a good dielectric union and the pieces of insulator material fall apart, the metal will start to touch and you'll start to have the corrosion occurring. So a dielectric union is what's used. All right, so the relative size of the anode and the cathode matters. And what we mean by that, not to say that the size of the pipe, but let's think about the size as the pounds of metal. Maybe the relative amount of pounds of metals compared to each other will kind of exacerbate or start to get this galvanic corrosion occurring quicker. So a large cathode, what does that mean? It means a cathode with many pounds of metal will generate a high level of electrical potential aimed at a anode that is relatively small in the size of the amount of total pounds of that metal. So when that current is aimed at a smaller amount of anodic material, we start to get pitting and pinholes actually in the copper pipe as well. It starts to increase the amount of corrosion within that copper pipe. So it's kind of interesting that the pipe itself will start to deteriorate because it's got such a high amount of galvanic activity. How you might want to think about this is if you imagine a home that has a lot of copper pipe that's coming from the water main and it's copper pipe underneath the house or in the walls. If you were to weigh the amount of copper that is in that pipe, you would have many pounds of copper. If you were to take apart the copper pipe and just weigh out the amount of lead solder that was used, it would be a much less amount of pounds of lead solder, or tin solder would weigh a lot less, and so that would be the big difference in the two different types of metals. So hopefully that helps clear that up a little bit for those of you trying to study for this. It's really not the size per se, say the size of the pipe. It's more about the amount of metal in pounds. So you can kind of see here in this picture, we see some corrosion occurring here and some green staining occurring at the copper. That also indicates that there's a large amount of corrosion occurring. Green staining tends to indicate that the copper is coming out of formation and is being exposed to the oxygen, which is making the patina or the green staining that we see here. We also notice a hole at the elbow here, a 90-degree elbow. So that metal is getting fragile, and any erosion corrosion that starts to occur because of high velocity will really start to make this pitting occur. And you can kind of see in this picture right here where this person is pointing to the pitting occurring on the copper pipe. Interesting to note here, we have a lot of copper line right here, but we also have some alloys right here where these fittings are. We see a union or a T coming off of there with different size pipe. And so that alloy, those are different alloys all touching each other right there. And the amount of the pitting is occurring on the copper pipe. So the copper may be assuming the role of the cathode, or rather, I'm sorry, the copper might be assuming the role of the anode over the other pieces of metal, which would be the cathode at that point. So some good examples there that you may come across. All right, so we're at our first place where we're going to have some questions showing up, and then I'm going to take a quick break. So here's the first question. It says, the location where the metal is lost in a corrosion cell and the tubercle forms is called what? Is it A, the cathode, B, the anode, C, the electrolyte, or D, the dielectric? Well, if you were paying attention and you're kind of following along with this, we would say the location where the metal's lost and the tubercle forms is known as the anode. Remember, that's where the lump starts to form. The cathode is a random place in the pipe. It's not where the tubercle is. The electrolyte is the actual water or the liquid moving through the pipe. And a dielectric is essentially an insulator. So that's why B is the correct answer. All right. Which of the following is not a type of corrosion? Well, we had a list a little bit earlier, and let's see if you remember what that list showed. We had 4 different types of corrosion showing on that list. And so we have A, electrochemical, B, polarization, C, galvanic, D, biological, or E, erosion. Now, these are all forms of corrosion. Which one is not a type of corrosion? That answer is B, polarization is not a type of corrosion, but A, C, D, and E are types of corrosion. All right, what is the term for an insulator used to prevent corrosion by separating 2 dissimilar metals? A, sacrificial cathode, B, sacrificial anode, C, inhibitor, or D, dielectric? I'll give you a second to think about that. Okay, time's up. And this answer is letter D, the dielectric. Dielectric is the insulator that separates the 2 metals. All right, so questions that you might have on galvanic corrosion. I hope that this was helpful to you to clear up some of the things that you might have read in the California Sacramento course material or the University of Florida's online course. We're showing a picture here at the point where I'm going to take a quick break, but we're showing a picture here of the Statue of Liberty. And the reason that I like showing this picture, it was a great example of galvanic corrosion that was occurring and was corrected many years ago. The galvanic corrosion had started to take place between the skin, which is made of copper, and the wrought iron metal that is inside the Statue of Liberty. The staircases and all that go up inside Lady Liberty are made of wrought iron, and when the 2 metals were touching each other, connecting each other, the iron was starting to corrode. So it was starting to fall apart, and the stairs and staircases and handrails and all that became unsafe. So they had to do a lot of rehabilitation. And the thing I found very interesting is when they talked to the state parks folks that did a lot of this work, they used the term dielectric, and they said, yep, we had to insert what's known as dielectrics in between the skin and the wrought iron structure to prevent this corrosion from occurring. And I thought, well, that's perfect, because I'm going to use that in my water treatment classes. So I'm going to take a quick break, and we are going to rejoin in just a minute. All right, I'm back. We discovered galvanic corrosion, and we covered electrochemical corrosion and a lot of definitions. I hope that everybody's hanging in there. So one of the things we just discussed before my break was the lead and copper pipe. And I want to mention to you guys that corrosion and its effects of or ability to corrode pipe greatly affect lead and copper deterioration in our water systems. So there's been amendments to the lead and copper rule, and as you probably know, there's more amendments coming in wake of a lot of lead and copper problems in drinking water around the United States. So the lead and copper rule covers things like corrosion prevention, the water chemistry measurements, the water quality parameters, and the things about galvanic corrosion that we just covered. So I just want to mention to you that we have these action levels that are part of our maximum contaminant levels from EPA and the Florida DEP. And one thing we want to make sure that you are aware of and do not forget is the MCLs for lead and copper. Lead is abbreviated on the periodic table as PB, and the MCL for lead is 0.015 milligrams per liter, also known as 15 parts per billion, or ppb. The copper has a action level. These are known as action levels, by the way. The copper action level is 1.3. These are primary standards, and copper is abbreviated as Cu on the periodic table, and the action level there is 1.3. That is known as a primary standard for copper. There's also 1.0 as a secondary standard. If a water system exceeds these levels in more than 10% of any of the samples taken, then the corrosion control action should be taken or must be taken. So we use what's known as the 90th percentile to calculate out or determine what the action level is. So when we talk about 90th percentile, what we mean is you would collect your samples. Let's say you collected 20 samples from your water system for lead and copper. You got all your results back. So then you take your results and you go through each result and you give it a ranking based on a number from 1 to 20. The way that I've always taught it is we start the number 20 sample is the highest result, and number 1 at the bottom of the list is the lowest result. So you're probably going to get a lot that are very, very low, and they'll make up the lower portion of these 20 samples that are ranked in order from the most to the least. And essentially what you would do then is say, well, what is 90% of 20? So if you took 20 and by that 90% or 90% of 20 would be 18. Sorry, I'm a little bit making sure I use my calculator here. So we have 18. So what then we would do is start at the bottom, number 1, and count up to number 18, or just your 18th sample that you've listed. If that 18th sample is greater than 0.015 or greater than 1.3 milligrams per liter, then control of corrosion action must be taken. So that's how you kind of do the 90th percentile calculation or determination. If you have any questions on that, or if I wasn't clear, please give me an email or call me. I'll be glad to kind of go over a little bit more thoroughly than we're doing here. But in a classroom setting, I tend to use a whiteboard and put all these numbers up and then have you do it. But we don't have that ability here with us right now. So the physical factors that influence corrosion are definitely the system construction. What that means is, what are the pipe materials and how old is it? The system pressure, what's the pressure that you maintain out there in the distribution system? Any moisture in the soil definitely tends to affect the makeup of the water pipes themselves. Stray electrical currents occur. A lot of times hot water heaters and things in the house are connected to water pipes, which tend to increase the galvanic or the electrochemical corrosion a little bit. The current temperature, water temperature, plays a big part in the ability for the water to be corrosive, and also flow velocity. We'll talk about erosion corrosion a little bit later. Temperature is an important one because temperature, cold temperature tends to make the water more dense and tends to slow down chemical reactions. Warm water tends to speed up chemical reactions. We also find that the warmer the temperature of the water is, the least or the less likely it is to be able to hold on to some of the components within it, say like calcium and magnesium. So hotter water tends to allow them to come out of solution rather than stay in solution. So we're going to definitely talk about that, especially with hot water heaters. Okay. So corrosion and its effects on system construction. The type of metals that make up the anode and the cathode. We already talked about the copper pipe with lead solder. Remember, we said a lot of it is really by the weight of each metal involved, and we talked already about the massive amount of pounds of copper versus a small amount of pounds of lead solder or tin solder. Um, the system pressure makes a big difference because gases tend to stay in solution better at higher pressures and then come out of solution when the pressures drop. So if you are familiar with, say, scuba diving and breathing atmospheric air at depth, and we are breathing that air at 80, 90 feet, it's going to have a different ability to stay in solution than it would if we were back at sea level. So the gases tend to come out of the solution when the pressure is released, which in many people are familiar with a term called the bends, when nitrogen bubbles come out of solution in our body. Well, think about this as what's happening in a water system. Higher pressures in the water system tend to allow for more corrosive gases to stay in concentration, and they come out of solution when the pressure is released. So CO2 and oxygen are two gases that we definitely are aware of that cause some problems with corrosion. In this picture, you actually see a fire system, and I took this photo at a hotel. And you see that the fire system pressure is maintained very high. The fire system water pressure is up over 150 psi, and that is always ready to go when a fire breaks out. So then the pressure would drop when the water starts moving and the valves are open and the sprinklers are on. The pressure would drop, and we would start to see some of that oxygen and CO2 coming out of solution at that point, similar to the bends of a scuba diver coming up too quickly from depth. So system pressure definitely plays a big part in the ability for water to be corrosive to metal pipe. And then obviously soil moisture. I'll just kind of mention this to you all, that that when you put a water main in a wet soil, or install a water main in a new area, and you have to use trenching and shoring, obviously, and then you have to use, say, like uh, a well point to keep the water, the groundwater out, well, then you know that that pipe is going to be submerged, so to speak, in a soil that's full of water. So the actual pipe corrodes on the outside rather than on the inside. I also have a piece of pipe here that I want to share with you guys that I brought with me from my little collection of stuff. And we see on the outside of a piece of pipe some corrosion that occurred on the outside. So the pitting and all that's occurring on the outside is generally from a lot of the soil moisture that is corroding and making the pitting, so to speak, in the anode and the cathode on the outside of the pipe. So that's just another example of that. So the soil serves as the electrolyte. The soil holds the moisture, and then that serves as the electrolyte. You can kind of see in this picture, this is a water main repair that was done here at the Trio Center many years ago. And we had a water leak, obviously, and they made a patch right here. They put a little band on there to kind of control that leak. But essentially, the soil moisture was deteriorating the pipe from the outside. So that's a good example of that. Let's talk about temperature a little bit further. Temperature plays a big part in chemical reactions, as we talked about a little bit earlier. And I do want to point out to you guys that that when you think about temperature and its effects on keeping things dissolved or in solution, maybe consider, like, if you were to make a batch of sweet tea at home, and you were saying that you really like that the water be warm when you put the sugar in, because it seems like it mixes so much better and it stays in solution and it makes the tea taste the sweetness that you like. Many people tell me that when they go to a restaurant and the server says that they have unsweet tea, that you can certainly use the sugar packets on the table. Many people say, well, that's not going to work. I don't want that because it's not going to taste the same. So that means that warmer water tends to allow for chemical reactions to occur more rapidly or more readily, which means the sugar dissolves. There is an exception to this. We want to make sure that everybody knows, especially those of you taking the B or the A, that as the water temperature increases, the amount of calcium carbonate that can remain dissolved in the water will decrease. Now, what does that mean? The calcium carbonate is actually what causes hardness. The hardness is in the water to begin with, and it's a part of our water column, especially in a lot of parts of the state of Florida. But when we heat the water up, the calcium carbonate that normally would make a slight scale formation on the pipe itself will now not stay in the water and will come out of solution. And where does that happen? It normally happens in hot water heaters or anything that when we boil water, or in locomotive engines when they were boiling water for steam, for the old steam locomotives, they would scale out the boilers or the hot water heaters excessively. It would really scale bad. So it definitely occurs more readily in our systems nowadays in hot water heaters and power plants. So we see a picture here of a plumber making a repair and coming out to check somebody's hot water heater. So the heating elements that you see in this picture, we see one on the top that's got some scale that broke off of it, and one on the bottom that looks a little bit cleaner without any heavy scale. And in this picture, you see some pressure sensors and pressure transducers that would be down inside of a water tank that are excessively coated with calcium carbonate, which almost looks like stalactites and stalagmites in some cases. But this is the calcium coming out of solution and adhering to those pressure sensors and heating elements. So that's where we readily see this occurring. And water temperatures, they get up over 130 to 140, 150 degrees, definitely will increase the amount of scale that occurs, and the water will, then the water itself will not have the calcium carbonate, and the water itself will be more corrosive. All right, so let's continue this discussion about chemical factors that increase or influence corrosion. A couple things right off the top here. We have alkalinity showing as a top one. We're going to talk about hardness and alkalinity here shortly. We're going to talk about dissolved solids and chloride and sulfate a little bit further. We won't spend a whole lot of time talking about the phosphate, silicate, trace metals, but I definitely know for sure that we are going to spend a bunch of time about this guy right here. So we have a few things important coming up for your studies. So alkalinity is known as a buffering capacity of water, or the ability of that water to, say, resist a change in pH, which would be a decrease in pH. So alkalinity is a buffering capacity against acids. And we can add acid to water, and if there's enough alkalinity, we won't see the pH change right away as far as decreasing because the acid's being added. So if alkalinity is present, it tends to keep the pH pretty stable. But once the alkalinity is used up, or once the alkalinity is consumed by the acids, and the acids overtake or overcome the amount of alkalinity, we start to see the pH fall. Now, alkalinity is made up of things like bicarbonate and carbonate and hydroxide, but they're also married or coupled to other things known as calcium and magnesium. So when we have calcium carbonate or calcium bicarbonate in the water, we have the combination of an alkalinity, amount of alkalinity there, and also an amount of hardness. Hardness and alkalinity are not exactly the same thing, but they are made up of similar components. Again, calcium bicarbonate, magnesium bicarbonate. So just want to make sure that we're clear on that statement. So if you're thinking about this and you're thinking, well, if scale formation occurs inside of a water main, or in my shower, or in my coffee maker, if scale is forming there, then it's actually coating the pipe. Well, that's very, very true. And they say here in this case that the simplest form of corrosion control or prevention is just adding alkalinity, or making sure the alkalinity is there just enough to coat the pipe to prevent the corrosive effects of the electrolyte to touch the metal. So it's a barrier. You can add a little bit of lime in a slurry, soda ash that's mixed up in a slurry. Caustic soda will give you a little bit of a boost, but not as much as lime or soda ash, or directly as calcium carbonate, which is known as crushed limestone. So again, lime is a common one. So if you were to try to prevent corrosion from occurring in a water main and you had a corrosive water, or let's say the Langler Index was at a low number, which we're going to talk about here in just a minute, then we can adjust that with soda ash or a lime slurry. So that's what we want to make sure that we're clear about. So that's a discussion about alkalinity. Now let's talk about pH. pH is the potential of hydrogen, and hydrogen ion itself is very corrosive at pHs below 4. If we have simply hydrogen ion in the form of, I'm going to just write it up here as H plus, which would be in a hydrogen ion form, it would be very corrosive at pHs below, say, 4. And low pH water tends to be corrosive in the environment of water treatment and water distribution systems. Low pH water would be anything for us really less than 7.0, 7 being neutral. pH of water that tends to be greater than 7.5 would tend to promote the scale formation ability of what's known as hydroxide. And hydroxide is essentially written out like this, OH negative. So when we have OH negative at a higher amount than we have H plus, which is hydrogen ion, we have a higher pH water, a little bit more alkali there, and it tends to be a little bit more scale forming, which would protect the pipe. So what are we trying to protect the pipe against? We're trying to protect iron and metal, like steel, against the corrosive component of water, as well as dissolved oxygen in that water. So I wanted to make sure that we're very, very clear, and you guys are studying good on this, that you remember that DO, dissolved oxygen, is considered one of the most corrosive components in water chemistry. The water itself is bad. The pipe itself, that's kind of crusty and all that obviously is bad. But if you have electrolyte or water with dissolved oxygen in it, you will speed up the corrosive effects of that water column. So dissolved oxygen reacts with at the anode and with iron, and it forms ferrous hydroxide and ferric hydroxide, which again is known as rust, and rust is the tubercle, and the tubercle is known to get bigger and bigger, and that whole process is called tuberculation. And then finally the anode, and it happens at the anode, and then finally the wall thickness of the pipe gets thinner and thinner at the anode, and then we have a leak in the pipe. So you can kind of see from that discussion and from this particular slide how important the component of dissolved oxygen is. So tubercles formed, water quality problems occur like red water complaints. The rust coating eventually slows down underneath the tubercle. It's interesting because the rust coating kind of slows down the interaction with oxygen until you flush the line. And then when we flush and we go out and we run all this water through the water main and we end up with a high velocity, we break apart all of these tubercles, and now we expose the pipe to fresh oxygen again, and the whole thing starts all over. So it's very important that we recognize this, that when it's occurring out in our water systems. So here's some good photos of red water complaints. And again, these are just photos that I found on the internet, just doing a Google search. You can find them on your own. It doesn't take long to come across pictures like this that people will take photos of and visit your city council meeting and complain about red water coming out of their taps. And if this is happening at your utility, then I suggest you investigate the problems with corrosion of your water mains, especially if you have ductile iron, cast iron, or steel water mains. All right, total dissolved solids, or TDS. TDS tends to exacerbate or help increase the amount of conductivity in the water. It's measured with a conductivity meter, and it allows for greater potential for corrosion when there's more TDS in the water. So when we add a scale, something to try to prevent corrosion, and we add, say, lime to the water, calcium carbonate would then give the water some TDS. They have to actually be there enough to start forming a scale but they only protect the pipe after they coat the pipe wall. So they have to almost come out of solution first or be dosed enough to allow them to start to kind of coat the pipe. It won't inhibit corrosion until it starts to make the scale. So some water hardness is actually helpful, believe it or not. Encouraging the deposition of calcium carbonate on a water main is actually a common method of corrosion control technique used in our water systems. Many people come to Florida and they tend to notice the amount of hardness in our water here. They see it in the coffee makers, when they rinse dishes, when you wash your car out in the heat of the day, and the water that you're rinsing your car off with has hardness in it. It will dry and leave white spots all over the paint or the windshield. Can be very difficult to remove because it gets almost baked on because of the high temperature, allowing it to come out of solution. One little side note that you might talk about here with your customers or even yourself is rinse your car off, and then either rinse it again with distilled water or use a squeegee to get that stuff off the water or off the windshield before it starts to dry on there, because it definitely will make a hard water film all over your car. So how do we measure the relative calcium carbonate saturation? Well, if we wanted to know how much our water was capable of making a scale, or how maybe corrosive the water is, we would then need to do something known as either a marble test or Langler Index calculations. And that's what we want to talk about now. Now, a lot of these come from the requirement to do what's known as water quality parameter testing if your water was shown to be somewhat corrosive, or if you had uh, broken or violated or gone over the action levels of the MCLs of the lead, which is 0.015 milligrams per liter, or the action level for copper, which is 1.3. So then we would be required to do water quality parameter testing and run these types of analysis. So the marble test is an interesting test. Now, it is covered in your Sacramento courses and in the University of Florida online course and other courses out there, but not many people actually do this test. It's very, very simple to do. It doesn't cost a lot, and you can do this on your own in your own lab. Really, the main thing you would need to do a marble test is calcium carbonate. I've got a bottle here, came from, this is Fisher Scientific. This is just calcium carbonate. And it actually even says on the label, natural chalk. So this is purified lime, if you will. It's just a white powder. It's actually lime rock that's lab grade or reagent grade. So that's probably not the type you would use out in the water system if you're a lime softening plant, but the idea is similar. So what we would do is actually inoculate a water sample with the lime or the calcium carbonate that we have, and we would test the water to see if it has the capability of holding more of that calcium carbonate, or if it's already saturated enough and it can't hold anymore and it comes out of solution. So all we're trying to do really is with a marble test to see, is the water able to hold on to more calcium carbonate, or is it already saturated and it won't, and it's gonna come out of solution and make a scale. That's all we're doing. Directly measures the amount of hardness or rather the calcium carbonate saturation is what we're actually measuring. So in this picture you see a couple of glass bottles. These are known as BOD bottles, or bottles with stoppers on them to prevent carbon dioxide from getting in, but they've been dosed with the calcium carbonate, and it makes that white milky looking solution. So the marble test is essentially where we would weigh out a small portion of the calcium carbonate. We would add it to a bottle of water with a stopper on it to prevent CO2 from getting in. And we would mix this thoroughly, several hours, maybe in half a day or more. And then we would let it settle out. We let it settle out for overnight purposes, maybe 8 hours or more. We're going to let it settle out. So what you're actually seeing in this bottle here, if I can use my highlighter here, you see actually a magnetic stir down here at the bottom, and it's the lime or the calcium carbonate has been settling, and it's making a little bit of a sludge down here at the bottom in that bottle. And so what we're going to do is we're going to run some analysis on the water right here. We're going to pipette some of that water out of there, and we're going to run it through a filter just to get rid of some of the extra particles. And what we're going to do is we're going to run some analysis on this water. What we're actually doing, if you don't mind, I'm going to back up just a second here, and I want to offer to you all that we need to measure several pieces of parameters rather before we add the lime to the water. What we're actually going to measure is the initial water. We're going to measure the pH. We're going to measure the hardness, known as calcium hardness. These are things that we're going to measure of the initial water. And then we're going to measure the alkalinity. Now, this could be the total alkalinity or the total and phenolphthalein alkalinity if we would like, but basically the total alkalinity. We're going to measure those three things on the initial water that we're sampling, and we're trying to see if it's got the ability to be scale forming or if it's corrosive. And then we're going to go through the motions of adding the lime slurry or the calcium carbonate to the bottle and mix it up. So we have an initial sample, results before we did this, and now we're going to come up with an after effect. So again, we're going to filter out some of that water, and we're going to run the tests again. So the results, what this means to us is that if the water was already full or saturated with calcium carbonate in the beginning, and we tried to force more calcium carbonate into the solution in that stoppered bottle, the calcium carbonate tends to come out of solution even more so than what we put in there. So the results actually show a reduction in the calcium hardness and the alkalinity of that water sample after we've done all this calcium addition. In a sense, if you're thinking about this from another process, in a sense, we're actually making a small lime softening plant right there on the bench top in that little jar or that little bottle. When we soften water with lime, we're essentially doing the same thing. We're removing hardness by adding more calcium. So in this picture, you can kind of see the effects of what that would do out in a water distribution system if the oversaturated water was allowed to go out into the distribution system. And you can kind of see from this how much scaling would occur on, or rather inside a piece of PVC pipe. This looks like C900 water main right here. You can kind of see the wall thickness right there of the water main, and look at the amount of calcium carbonate of deposition on there, and it's in different layers. It almost looks like the rings of a tree, and that piece of 8-inch pipe is down to maybe less than a 4-inch overall inside diameter now because of the heavy scaling that's occurring. So this would be an example of a very high Langler index number, or a very scale forming water, which is almost to a point of over scale formation. We don't want that to occur out in the system. Undersaturated water, on the other hand, would lead to aggressive water, also known as corrosive water, which would not deposit a protective calcium carbonate film, and then would maybe even deteriorate any calcium carbonate and corrode the pipe. So undersaturated water would mean that the effects of the marble test were that the water, the initial water, was undersaturated, and it wanted the calcium carbonate in it, so it dissolved readily into the water. And when we measured the hardness and alkalinity again, those values went up from the initial water. So if the initial water sample results are A, and then we come around and we do the second one and we say that the B results are even higher than the beginning, then we know that the water was essentially the initial water was corrosive. So I hope that's helpful to you all, because it is definitely something you need to know for your exams, all the way from the D, the C, the B, and the A. So let's take a look at some other results here. you'll notice that it says if the pH, the calcium hardness, or alkalinity have increased. Now, it increased from the initial sample, and then we remeasured again after the dosage of the lime or the calcium carbonate. Then the initial water was undersaturated, which means that it was corrosive. If the pH, the calcium hardness, or the alkalinity, or all three have decreased, especially the hardness and the alkalinity, if those have decreased, then the initial water was already saturated or was super saturated, and it allowed this stuff to come out of solution. So it was already at the saturation point. So that water would be scale forming. If the pH, calcium hardness, and alkalinity essentially remains about the same. Now, the numbers might vary slightly from each other. Let's say a hardness of 200 versus a hardness of 201, or a hardness of 199 at the end. Well, then we would say, well, that's essentially the same. It's within a small percentage of each other. And we would say that that water is at saturation, it's stable, it's not really going to make much of a scale, but it's also not going to be corrosive either. So that's kind of what we're looking for in a sense. We're hoping for water to be slightly scale forming to be protective of the water mains. So take a look at some results we have here, marble test results. We see an initial pH of 8.7, and the initial calcium hardness was 34 milligrams per liter. Now it sounds kind of low with a pH of 8.7, but the initial calcium hardness was around 34 milligrams per liter. So not a whole lot in there. When we added the calcium carbonate and we dissolved it and we let it settle out and then filtered it and blah, 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 we come back and we say, all right, let's check the pH. Oh, pH went up to 9.1. Well, that's a pretty good increase. And the hardness actually increased up to 38 milligrams per liter. So the hardness increased. So what are the results telling us? The results are telling us that the initial water, this water, was, drum roll please, undersaturated and therefore considered corrosive. So it wanted the extra calcium and it was able to hold on to it. So that is how those results would be interpreted. All right. Langler Index is also a way that we discuss water corrosivity, or Langler Saturation Index as far as calcium carbonate saturation. Langler the Langler Index is considered stable when the water is just at saturation with calcium carbonate. Remember that. And that water will neither deposit, make a scale formation, or even corrode the pipe itself when it's at say a neutral number. And in stable water, the calcium carbonate is in equilibrium with the hydrogen ion. Remember, we said hydrogen ion was the H plus, and the calcium carbonate is a -2. So when those are stable, they are kind of equalizing each other out. So a positive result, or a positive number of Langler saturation index, would indicate that the water, the initial water, is super saturated and will form a scale. So any number that we get with Langler index above 0, if we look at a scale of say 0 being neutral, and we have a scale here, we go up and we go down. I'm kind of drawing out here on my little tablet over here. We have a 0 Langler saturation index. So if we go up on the plus side, or the positive side, let's say 1, 2, 3, 3, 2, 1 here, and then -1, 2, 3. So we have -1, -2, -3. When we go up on the positive side of the Langler index, we are considered scale forming or supersaturated. When we're on the negative side of Langler index, we're considered undersaturated, and therefore the water is corrosive. So we really don't want to be in the negative realm. We'd like to be, I would say we'd probably like to be kind of right in that range, right in there, just slightly scale forming, so that we're protecting the pipe. All right, so how do we calculate Langler index? Well, there's a formula, and the formula is shown on the formula sheets for your state exam. It is there. I think it's under laboratory analysis, and it's listed as Langler saturation index, or Langler index itself. And the formula reads just as you see it here. It says pH minus pHs. Now, don't want to confuse the issue any more than maybe you already are, but the pHs is a number that's given to us, and that it's actually calculated from several factors. The pHs takes into account the water's temperature, the calcium hardness, the TDS, and the alkalinity. And those are calculated together and subtracted from the initial pH number that we have to give us a factor known as a pHs. So it's a sub number, or it's a sub calculation that's got some other things to it. Now on a state exam, you don't have to do all of that. You don't have to worry about, calculating pHs. They give it to you on the state test. But I just do want to point out to you that that's what the S is standing. It's a different type of pH measurement that has some calculations done within it. So the pH is derived from several factors. Now you see in this example, we have an 8.6 pH and the pHs is 8.22. So essentially, we're just going to subtract from the 8.6, we're going to subtract 8.22. And that on your calculator will give us 0.38. Now on your calculator, if you're working this one out, you will not see a negative symbol showing up on the display. It's just it's a positive number, so there's no negative display. And it's kind of simple to see that when we subtract a smaller number from a bigger number, we're going to get a positive result. So we have a positive. We could put a little positive symbol here to say that it's the positive side, but that Langler index indicates a slight scale formation ability of the water, or not corrosive per se. How about this example? We have 7.8. I'm going to write it out like this. We have 7.81, and again, subtract from that 7.96. And you have to write it out exactly as it's shown so that we do get a negative symbol if it is actually negative. So 7.81 minus 7.96, and I get a 0.15, but a negative factor. That's a negative 0.15. So it is on the negative side of Langler index, which would probably mean that the water is slightly corrosive or is not scale forming. All right, so there we go. We got the numbers plugged in. The condition of the water is considered corrosive or aggressive. So that's how we do Langler index. All right, hopefully that was not too painful. All right, what's the condition of water? We said it was going to be corrosive. So let's move on. Other factors that influence corrosion. We have bacteria that are all over our planet Earth. They live down in the well water, from the soil. The deeper you go into the wells, and deeper wells tend to get into areas where there's more iron reducing bacteria, sulfate reducing bacteria. They're naturally occurring in soil, and they get pulled up into the water well or through the water intake structures. They can actually start to coat the pipes themselves. They can get caught in the water system. They can get caught up in backflow preventers, things like that, and start to grow colonies on the pipe wall itself. The actual pipe wall could get a slight slime formation or bacteria formation on the pipes. Now, they're not pathogens, but they definitely would impart potentially a smell to the water or color to the water. Color with iron bacteria generally gives us a reddish tint to the water, and sulfate reducing bacteria give us a little bit of a blackish tint to the water, or even a rotten egg odor. So iron bacteria grow in a filamentous form. That means a hair-like structure, hairy types of bacteria chains. And they result in a slimy, reddish mass that sometimes gets in the water wells, on the well screens, in the well column, or even up into the water system itself. They form in a couple of places, obviously, in storage tanks and all. The bacteria themselves are shown here. The parentheses is kind of, or rather italics, is just showing us the genus and species name. Crenothrix, Spherotilus, and Galeonella are the genus of the bacteria. and it make this like reddish tint. Now this little water bottle has been tilted to the side. You can kind of see that the water level is right here, and as they tilted it to the side, it kind of exposed that reddish film that's growing inside that bottle. That would be a filamentous type of iron reducing bacteria growing in that sample bottle. The deposited iron can be released during periods of high flow, which tends to give the red water complaints. It gives a musty smell. Sometimes people complain that it smells like a musty, like a sewage smell in some cases. The corrosion definitely gets accelerated underneath these deposits, these slime layers, because they excrete acids, which tends to attack the metal of the pipe underneath the slime layers. So it's actually very important that we keep our water mains maintained, and occasionally flush, and occasionally pig them or swab them if needed, especially if we have iron pipe that's giving us or wells that are giving us some iron reducing bacteria and causing some taste and odor problems. Sulfate reducing bacteria are famous for giving us the distinct rotten egg odor in the drinking water. They react with metals to cause black metal sulfide deposits, which people tend to say that the water looks black, or even in the toilet fixtures themselves, they'll see a metal, or rather the black staining of the porcelain structures. And some of that is the hydrogen sulfide being oxidized by the chlorine residual in the tap water, or the chlorine tablets that are added by residents and homeowners to try to keep the toilets clean. Dead-end water mains are definitely places where these things can grow. So with the low flow in a dead-end water system, or in spaces around, say, valves, or in auxiliary lines coming off of the water mains that go to hydrants, those 6-inch water lines that come off of a big water main are essentially dead ends where water just sits there and somewhat gets stagnant. And anaerobic bacteria, and again, some of these iron reducing bacteria and sulfate reducing bacteria are considered facultative anaerobes, and they generally start to create foul odors and the definite color problems. Most of you probably have seen this if you've ever been out on the job when you're flushing water mains, and that first blast coming out of a hydrant looks nasty and it has odor to it. That's because these bacteria are growing in the dead end areas, or also known as annular spaces of valves. So when you first go out and open up a hydrant, the first blast can come out somewhat discolored. Now this one doesn't look too bad in this picture, but think about any holes in the pipe surface from pitting, any places up inside of valves, and in hydrants especially. All right, so hopefully that covered some things that you were curious about with chemical factors that influence corrosion. Let's take a look at determining if corrosion problems actually exist. So we're going to talk in this segment about coupons, sections of pipe that have been taken out, when you've actually repaired water mains, flow testing, and essentially chemical testing. All right, so coupons. Coupons are not the same thing as going to the grocery store and getting 15 cents off of a bottle of Dawn dishwashing detergent, or whatever you happen to be using a coupon for. The coupon here is actually a piece of metal that is a specially made piece of metal that's inserted in a water main that has a definite known certified weight and a certified dimension. And we insert these pieces of metal into a water main and allow them to be in the flow of the water for a period of time. That could be a month, it could be 6 months, it could be a year. And after a time period, the coupons are removed. We weigh them and we measure them again with a micrometer, and we see, did they gain weight or did they lose weight, or did they stay exactly the same? Now, the rate of corrosion is determined by the loss of the weight and the size of the coupon between the weighing intervals. So what that means is that the coupon would lose weight if the water is corrosive to the metal. The coupon would gain weight if the water was scale forming, and it would gain size as well. So you can kind of see in this picture several different types of coupons. In the far left would be threaded. This is a threaded piece of metal right here that could be threaded into the water main or into a corporation stop on the actual water main itself, and this shaft is down in the water flow. You can kind of see the shaft there. Now, a nice clean one, like in letter B, looks nice and clean, and in letter A, it looks like it's pitted and kind of broken apart a little bit. That water was slightly corrosive. And then over here on the far right side, you see different uh, types of coupons. These are weighed. They have a significant, or rather a special weight to them that is known by a certificate. And we also have a dimension of that little paddle thing, and that would hang down in the water and then either gain weight or lose weight. A coupon is also known as a piece of pipe, a circular disc of pipe that would come out of a water main after you've done what's known as a wet tap or a tap under pressure. When we do a tap on a water main to install a service for a customer or some type of installation, we generally use a machine or a drill that has a large cutting head on it. And it kind of reminds me of a hole saw that you might use for drilling a large hole in something and hooking that to your drill. So this hole saw is a part of a structure or equipment that's strapped on to the water main, and then slowly, either by hand, which is how I had to do it back in the day, or with a machine, with an electrical motor, it actually turns and turns and turns and essentially is cutting a piece of the pipe. And with it being hooked onto the machine itself, it's kind of sealed. Now, when you pull that machine out and pull the bit out and then shut the corporation stop off, or the valve on the saddle that you're using to make this tap, when you shut that valve off and extract the machine out of there, you should be able to look up inside of that hole saw and see the piece of pipe. If you don't, that means it fell into the water main and now it's tumbling along and it's going to cause a clog somewhere at some point. And you're hoping that that's not the case. But you want to find that coupon inside the hole saw. And I think it's particularly important to retain those. And I would actually keep those in a special place where you could maybe write the time, the date, and the location on the one side that was actually the outer diameter, and then be able to see the inside, because that's actually a little sample of the inside of your water main. So with the time, date, and location known on it, when you go back later on and do some work there, maybe downstream or upstream, or you have a water main break and you get another piece of pipe out of there, you could actually look at the differences and compare the coupon that you pulled out of there from your wet tap versus later on one that was done a year later or whatever. And you could actually physically see the results of either corrosion or scale formation. I just think that's kind of a helpful tip from me to you. And I only learned that from my father, who was a water treatment plant operator back in the day. So I learned it from him, and I'm passing it on to you guys. Okay, so chemical tests, including dissolved oxygen. Water supplies that come from a surface water, like a reservoir, will contain dissolved oxygen. It's just naturally occurring in nature. With algae, algae produces oxygen. Oxygen gets into the water. It actually also comes from other places like wells and things like that. Sometimes have air releases that allow a little bit of oxygen to get into the water main when you first kick it on. Anyway, this oxygen's in there, and when oxygen and water and iron get together, they make this nice thing called rust, and that's what we're trying to prevent. So if you were to measure dissolved oxygen from, let's say, in a water main that is several miles long and it's made of galvanized metal or galvanized iron or cast iron, if you were to say start at the water plant and measure the dissolved oxygen and you got a residual oxygen of say 6.0 milligrams per liter, and you went 2 miles downstream on the same water transmission main and the dissolved oxygen was now say 2.0, and you lost 4 milligrams of oxygen somewhere, that would generally indicate that corrosion is occurring in there, because the oxygen is being used to make the rust. So Just want to point out to you that this is a very important statement on your studies, for your drinking water exam. Do not forget the corrosive component that oxygen plays. Um, all right, so ways to reduce corrosion. Well, we can prevent corrosion because if we can keep the oxygen out of the water, that might help us prevent corrosion. If we can keep the water without any total dissolved solids in it, that might help us prevent corrosion. But both of those two things I just mentioned are almost impossible. So we have to come up with other ways to reduce corrosion or prevent corrosion, so we don't have holes in pipe like this or red water complaints like this, and a lot of tuberculation. So a couple things we can do to prevent external corrosion would be to wrap the pipe in a polyethylene liner before it's actually buried in the ground. So a lot of water systems contract out the installation of water main pipe, and large diameter water mains that are made of ductile iron or some type of iron will in some cases come with a wrapping material that's put around the pipe and then heat shrinked to reduce external corrosion. It's supposed to protect the outside diameter of the pipe from the electrolyte, which is the wet soil. So you see some pictures here from one of the websites of a contractor that does this kind of work. These are some pretty large water mains, and they would be wrapped with this polyethylene liner and then shrinked down to give some protection against the soil. Now remember that if this is damaged in any way or compromised in any way, then water could get up underneath that liner and damage it. So we have to be careful that we make sure we do accurate line locates for people that are doing like boring of telecommunication systems or cable systems, things like that. If they strike this pipe and damage that liner, then water could get up underneath it and start the corrosion to occur. Zinc compounds are famously used. We have several that are used, like I mentioned, steel pipe earlier can be coated with a galvanic protection, which is essentially zinc that is melted, and the pipe is coated with that. Zinc compounds can also be purchased to form a film that makes a cathodic protection film inside of a pipe. These zinc compounds are proprietary. That means that you must contact a vendor to come out to your location and usually give you a dosage. The chemical would be added to the water to form this slight film in the pipe. Um, they are a little bit more expensive than, say, just adding lime slurry to the water, which we talked about earlier. They are less scale forming. The zinc compounds are less scale forming than, say, adding lime. Obviously, we want to watch out for that. So this might be preferred by your water system because you don't want to form scale. Zinc phosphate compounds that contain zinc and phosphate together should not be used in water that would be stored in a reservoir that's exposed to sunlight, because the phosphorus would actually increase algal blooms. So we generally don't use the corrosion prevention chemicals out in the reservoirs, but that's just something we wanted to make sure that you see there, because the phosphate component would definitely increase algal blooms. But one of the advantages of using a zinc compound, a zinc phosphate compound out in a water system, is that chlorine residuals tend to be more stable and last a little bit longer out in the far reaches of the water distribution system. So total chlorine residuals or free chlorine residuals from the water system tend to be a little bit more stable and last a little bit longer out there, especially when using zinc orthophosphate, which is ZOP. Zinc orthophosphate, again, is a proprietary chemical, and you can always contact a chemical vendor to investigate this. Now, again, the chemical vendor will probably want to visit your facility and do some water quality analysis to see what would be the best product that they have for you. Some other chemicals that are used are sodium polyphosphates. Sodium polyphosphates have multiple, which is the poly part, multiple phosphate atoms there, and the compound itself is made of sodium and polyphosphate. So we see in bullet point number, or this bullet point here, we see sodium hexametaphosphate. Very common chemical to use out in a water distribution system. Sodium hexametaphosphate will form a protective layer on the pipe and protect the pipe. But it does also react with calcium hardness that's already in the water, which would then reduce the calcium carbonate concentration and potentially interfere with the ability to make the scale on the pipe or even the film on the pipe. So this is why it's important that you as the operator or you as a water system manager recognize that we can't just run out and say, hey, let's go buy a drum of polyphosphate and add it to the water system. This does take a little bit of bench testing to make sure that you have the right chemical components for that particular chemical that you might want to use. So it could actually increase corrosion because it's reacting with calcium hardness and reducing the ability for the scale to form. So this would be a great troubleshooting question that you probably would want to pay attention to on a B level exam or an A level drinking water exam, because not all polyphosphates are going to fix the problem. Sodium hexametaphosphate can be found in a couple of different formulations, generally as a dry chemical in bags or in a liquid. They also help do something known as sequestering. They can be used to mask red water problems. Let's say you have well water with iron that does show red water component to the water. A sequestering agent, I'm going to underline that. A sequestering agent is a chemical that bonds with the iron in solution and keeps it in solution and prevents the oxygen from causing the red particulate matter to come out of solution and show itself. So it's very common to add a chemical as a sequestering agent to prevent red water complaints. So you see in this particular case, a proprietary phosphate blend. This is known as Aquamag, which is a blended phosphate solution. And this is one that we use at the water plant in the town where I live. So any questions on corrosion prevention? I'm looking around. I don't see anybody asking questions, so I'm going to continue on going. I think we have one more or several series of questions here. But before I show you some of these questions, I just want to point out, I'm going to go back a slide here. If you all can take a look at this picture, you'll probably recognize that these workers are, looks like they're making a water main repair. And notice that they're down in the ground. They've got trench shoring and using good barricades there. They're following all of the hard hat rules. They're using personal protective equipment, and they've got a ladder in that trench. That would be a good example of making a repair in a safe manner. So you'll want to follow any kind of safety precautions that you can whenever you're working in this kind of this stuff. I know that we're trying to get the job done quickly and get the water main back up in service, and everybody's complaining that they're out of water, but we have to do the job safely. All right, let's look at some corrosion control questions. Which chemical can be used to mask red water problems by bonding with iron, but could increase corrosion by reducing the effective calcium carbonate scale forming ability? Is it A, sodium hypochlorite, B, sodium hexametaphosphate, C, hydrofluosilicic acid, or D, zinc orthophosphate? So I'll give you all a few seconds to think about that one. And time's up. This answer is B, sodium hexametaphosphate. We just talked about that a few seconds ago, so remember that one. How about this question? The operator of the water system is experiencing an increased amount of water leaks in the distribution system, and lab results for lead and copper show both have increased over time. The operator suspects that corrosion is taking place in the water distribution system. Which lab tests listed will help confirm that corrosion is taking place? Is it A, dissolved oxygen, TDS, and temperature? Is it letter B, temperature, pH, and ammonia? Is it letter C, dissolved oxygen, alkalinity, and temperature? Or letter D, dissolved oxygen, the marble test, and coupon analysis? So there's several here that look pretty good. This one always draws some people to incorrect answer choices because some of these look really good. Notice that dissolved oxygen is in 3 of the responses that are given. So I'm going to guess that dissolved oxygen is probably pretty important. And I don't recall that we ever mentioned anything about ammonia in the actual discussion. So I'm going to say that B is probably not a good answer. But that leaves A, C, and D. Now, what about A, C, and D? Now, we did talk about alkalinity, we talked about TDS, we talked about temperature. What are we trying to do with this question? The question says, which lab test listed will help confirm that corrosion is taking place? Now, remember, we're trying to confirm that it is happening, not does it have the ability to happen. We're trying to confirm that it is happening. All right, so coupon analysis. It is a confirmation. Remember, if the coupons have lost weight, they will confirm that corrosion is taking place. The marble test. The marble test is closely linked to the Langler Saturation Index. The marble test is a benchtop test to see if the initial water will actually hold more calcium than it already has. And D, or rather D shows dissolved oxygen, which again, measuring dissolved oxygen before and after the locations that we suspect corrosion is happening is a way to confirm that it is taking place. All right, that's why answer D is the best answer. That's a tough one. All right, how about this question? Special steel specimens called coupons are inserted into a water main. After several months, the specimens are removed from the main. All the coupons have gained weight over the period of time. What does this indicate? A, the water is scale forming. B, the water is stable. C, the water is undersaturated. Or D, the water is corrosive. So if, again, you're not sure of this, remember that there is only one correct answer for any of these choices. And if you see something that looks kind of fishy to you and you say, well, don't some of these responses mean the same thing? Like, let's say, for instance, corrosive water would be undersaturated with respect to calcium. So C and D essentially really mean the same thing. And letter B says the water is stable. Now, we pulled the coupons out of the water main and they gained weight. So something is happening to them. So letter A is the best choice. The water in this case is scale forming and it's causing the coupons to gain weight. All right, now you guys have successfully made it to the end of the corrosion control segment. If you're listening to this and you're watching along, I thank you for bearing with me. You also probably have found that when you've completed this section in the California course, this is the Sacramento Volume 1 section on corrosion control, kind of showing you that picture here. This manual has a statement at the back of this chapter. If you haven't seen it, maybe you didn't read all the way through the chapter and didn't come across the statement, but the statement in the California book says something to this effect. It says, "Congratulations, you have made it through one of the toughest and most chemically complex sections of our course." And that is very true when it comes to studying for your state exam. There's a lot of components with corrosion control. You might feel like this right about now. Now, I'm not condoning drinking. I'm just saying that old picture from Animal House kind of maybe maybe says, "Congratulations, we're gonna relax right now," right? Anyway, so I want to thank you for watching this session. My contact information, as always, is behind me on the wall. You can kind of see it posted there. You've seen it the whole time. It's also shown here on this slide. Thank you for watching. If you have any questions, again, the best way to reach me is generally at the trio.ufl.edu email address. And I hope that this was helpful. Let us know how you do on your state exam. If you have questions, please call or write me. I appreciate it. Everybody stay safe and healthy out there. We're getting through this together, right? Take care.